I'm Michal Mizrahi. I'm at Iowa University. I'm a second year master's student at the Oxides lab, and I'm going to talk to you about the development of PDM-free materials for OER in an alkaline environment. So, as we heard of the fuel cells, which is the use of hydrogen, now we're going to speak about actually producing hydrogen. So before getting into it, to understand why it's important is, as we know, we have a need to shift towards renewable energy, and this is because peak global warming rates here we see in average temperatures from the 1900s till today. We see that the global warming rates are significantly increasing. So we know that it is due to using combustion of fossil fuels, which release detrimental gases, in order to meet our energetic needs. So, and as we've heard, this is where hydrogen comes in. So currently, the only use for hydrogen today is petroleum refining and ammonia production. However, by shifting to using renewable energy and making it a more competitive production of hydrogen, we're going to have the hydrogen application expanding to many different sectors, especially the transportation sector, which is what I'm doing today. And the way that we can, the thing that we heard today, that the problem with shifting our energy economy to relying on renewable energy is that the main issue is the storage of this energy. Meaning you have ample amounts of the sun and wind power, but those are only available at peak hours and in optimal conditions. So in order to truly be able to utilize that energy in a sustainable way, we need to store it in the form of hydrogen. So currently, the way that hydrogen is made is not only through renewable energy, but it's also made through, just like all of our energetic needs, is through the combustion of fossil fuels. However, we do want to shift it to starting to make hydrogen through renewable energy, and the way that this can be done is in the help of electrolyzers. But, so we've established that it's green, but the other factor that we have to consider when talking about hydrogen is also, is it safe? Because I know it has a bad name for being not safe, given Hindenburg disaster. However, when thinking about gas safety, there's actually three parameters that are essential to look at: the diffusion, the buoyancy, and flammability. So the farther from the origin of this graph, the safer it is. Meaning, given that hydrogen is the lightest element on Earth, it diffuses very quickly and it's very buoyant, as opposed to other gases that we use today that are very heavy and way down. Here, the DOE did an experiment where they have a car with a tank with hydrogen and a car with a tank with gasoline. And they purposely punctured the tanks and ignited the cars. So with the hydrogen, we see that it diffuses very significantly. It doesn't stay at the site of the puncture and at the site of the car. So within 60 seconds, the flame mainly just is gone, and it diffuses and disperses. However, with a gasoline engine, it's very heavy. It does not diffuse and it's not buoyant. It's weighed down by gravity and stays at the site of the accident. So it almost in 60 seconds causes the whole entire car to be completely inflamed. So when we're talking about hydrogen, it's not only safe, but it's also green. So given this, it's one of the main chains in producing a sustainable green future. So as we said, we can take the otherwise wasted renewable energy, form hydrogen, and then use it from, as we heard, using fuel cells to power our energetic needs. So now we're going to talk about how, in fact, we use this renewable energy to make hydrogen. So there are many electrolyzers, just as with fuel cells. There's acid, alkaline, solid oxide. But today I'm going to be talking about alkaline electrolyzers, and the reason for this is that we not only want to produce green hydrogen, we also care about how much it costs. So alkaline electrolyzers allow us to use PGM-free material, so we can stay away from iridium and ruthenium, which are very expensive and scarce on Earth. So with alkaline electrolyzers, PGM-free material are stable. So here, the electrolyzers uses some source of energy, hopefully renewable energy, and it uses that energy in order to perform electrolysis, which is the splitting of water into hydrogen and oxygen gas. And here we can see the basic scheme of an electrolyzer, and we have both of the coupled reactions, the oxygen evolution reaction and the hydrogen evolution reaction. So while we're speaking that we want hydrogen evolution, but we know that the hydrogen evolution reaction cannot be done without having oxygen evolution. And here, oxygen evolution is a complicated 4-electron process, and it's the sluggish reaction of the two. So the research is focusing on increasing the kinetics of the oxygen evolution reaction with the help of catalysts. Now, currently, the leading catalysts in the field for PGM-free material are nickel iron oxide hydroxides. And the form that they take on naturally are lighter double hydroxides. The reason why these materials are the PGM-free state of the art is because they have this intricate structure that is layered, and which each layer contains charged metals and metal hydroxides, where in between they have anions and water molecules to balance out the positive layer, which contains the metals. So this allows us to have a high surface area of the catalyst to be a high surface area, and also to have the ability to easily exchange anions that we wish to react in order to produce hydrogen, meaning that our precursor for hydrogen is OH minus. And given that within the structure already there are these molecules, when it's reacting, it's able to easily exchange into it and react. So while this is the state of the art currently, it's not good enough and it's not as efficient. So my work is to further make the activity of this material even better. And I'm doing that in one of two ways. So the first way is to increase the surface area, which is going to be done by synthesizing this material as an aerogel. An aerogel is one of the lightest solids in the world. It's composed of almost 99.9% fluid volume, meaning that here in the central picture we see the weight comparison of nickel cobalt iron oxide compared to nickel iron cobalt oxide hydroxide, which is the powder form of the aerogel. And we can see that these are the same exact weight, but the volume difference is very significant, and it's solely due to the fact that there's more volume within the surface, giving it. So we can see here that it's a very porous network, and because of this, we have a very high surface area of our catalytic material, which obviously is beneficial given that higher surface area means higher catalytic active sites, meaning higher activity. The second way that we are increasing the surface area of the nickel iron oxide hydroxide is by adding an additional metal. Cobalt is shown to further stabilize the material and also increase the activity. The exact active site is not very much agreed on. There's not been a lot of work done on it, but it does show it improve, as we'll see later on. So this is essentially how we make the aerogel with the cobalt and iron and nickel, so the 3 transition metals. So it's a very specific process in order to make the aerogel, and it's made by a sol gel process, meaning that we're making the gel first with with a solid with liquid dispersed throughout, and we dry it in a supercritical way in order to remove the liquid within the pores and causing the internal structure of the aerogel to not collapse on itself and to be spread out and maintain its high surface area. So through BET analysis, we currently have made 7 samples of the aerogel to show firstly the effect of cobalt, with each increasing number of aerogel increasing the amount of cobalt that's being added. And we see on the whole that all the aerogels are almost 5 times the amount of the surface area than the nickel iron cobalt oxide hydroxide, showing that the surface area does in fact significantly increase when forming them in the form of an aerogel. Here we see the activity, so not to overwhelm you, but we see a few things in the activity of these materials. So first we can compare all the aerogels to the nickel iron cobalt oxide hydroxide. This is the powder form. So we can see that it significantly outperforms the nickel iron cobalt oxide hydroxide, and we can see that this increase in activity is due to the increase in surface area. Additionally, we can also see it compared to the PGM state of the art, iridium oxide, and we can see that one of the samples actually outperforms the precious metal. And the other thing that we see here is that with with an increase in the cobalt content, we see an increase in activity as well. Meaning aerogel 7 has the greatest amount of cobalt, and we see that it has the best performance. And the last thing that I've done is heat treat this material. Given that it's very porous, it's likely that there will be a lot of hydrogen, a lot of water within the pores of the aerogel. So after heat treatment at 100 degrees Celsius, we see that there is a significant color change and also an activity change. There has to be more work done on it, but essentially we do see that for the most part the activity does increase somewhat or stays the same, and we attribute it to this also having more active sites given that the water has left the pores of the aerogel. Thank you.
Thank you. Nice presentation. Questions?
So, excuse me, so that was for the whole ER, right?
Yeah.
Yeah. So, what catalysts do you use typically for the HDR?
So, some of these materials, I don't focus on HDR, but for PGM-free materials, the nickel, iron, in different forms with different metals. Some use titanium. Some of them work towards being bifunctional catalysts, but usually when people are focusing on the OER, they're usually just using platinum on carbon for the hydrogen side. But there are promising results for PGM-free material also for the HER, but it's not really a focus given that the OER is really the bottleneck of this reaction. So by increasing the kinetics of the oxygen, the production of hydrogen isn't going to be a problem.
Did you test the catalyst already in the small cells?
So in a half cell, as I showed the civic
Clear water electrolyzer.
So we actually just got one of the new state-of-the-art alkaline electrolyzer, one of the first that were made. It's very new, so not most of the studies have been using polymer electrolyzers, but we've started to test them. Yeah.
So you can look the results.
Sorry?
Do you have that? Do you have results that I'm not sure?
Not that I can show yet, but
Okay.
yeah, it is being tested and it looks promising.
Which membranes do you use?
We're using reinforced anion exchange membranes.
Which membrane?
From which company?
From where? Yeah.
We've ordered them from Wyoming.
Okay.
ABL.
Yeah. So we're using reinforced anion exchange.
Okay. So, first of all, we can test it in our lab. You want to compare with state of the art. Second, the comments when you saw in the RD, you have 1 molar QA.
Yeah.
I strongly recommend to also characterize 0.1 molar. This is the state of the art.
I have done.
We all move to lower and lower concentrations.
Yeah.
That's good to have data.
Yeah. All the tests that I showed from 1 molar, I've done them also at 0.1. So it's the same trend, but given that it's 0.1, it's a little less accurate, but typically it's not as.
Yeah, that will be very soon the state of the art, so we will be required to show that data. Any other questions?